Hello everyone. So in this lecture, I'm going to talk about stream functions, which are actually going to help us to find analytical solutions for some simple two-dimensional fluid flows in an invested world. Okay, so let's get started to see what they are. So for a two-dimensional 2D incompressible flow, we can write the continuity equation as follows. So it's going to be divergence of velocity is going to be for a 2D flow, it's only in the x and y direction, so partial u partial x plus partial v over partial y equals to 0. Okay? So now based on this, we can then define a function psi such that u is partial psi over partial y. So partial psi over partial y is just u, and then minus partial psi over partial x is velocity component in the y direction, or v. Okay, so this is just a definition. We define psi like this to satisfy the continuity. So let's see how. So use continuity now. So this function, first we have partial over partial x of u, right? So instead of u, I'm going to write this from here. So I use partial psi over partial y. And then I have plus partial over partial y of v, which is going to be minus partial psi over partial x. And as you see, this is going to be partial square psi over partial x partial y. And these two terms are going to cancel out, and this becomes 0. So this psi or stream function, which we call it stream function, psi, is defined such that the continuity is always satisfied. So this is defined based on a continuity equation for an incompressible flow for a two-dimensional flow. Okay? As you see, this is defined such that the continuity will be always satisfied. So now let's investigate some of the properties of psi, and let's see what do actually they mean physically. So let's start properties of psi. The first property is I want to say what are these psi, like what does this psi mean? So this psi, if it is constant, let's see, for a constant size, what do they actually represent? They actually represent streamlines in the flow. And we can prove that. So let's look at it. So d psi is going to be the delta the differential of psi, because psi is only a function of x and y, right? It's a function of x and y, so it's going to be partial psi over partial x dx plus partial psi over partial y dy. And what are these? So what are these? Based on here, the definition of that, so partial psi over partial x is going to be minus v times dx plus partial psi over partial y. From here, it is going to be u, so it's u dy. And let's investigate this d psi for a constant psi. So let's say we are on a constant psi, and we want to see, like for this constant psi is constant. What does that represent? So if psi is constant, then the d psi is going to be 0 because we don't have any changes in psi along this line. So this means that this is going to be 0 for constant psi, or psi equals to a constant. Okay. So now let's see what does this entail. So for psi equals to constant, we have from this equation dy over dx equals to, I take the v dx to the right hand side and then rearrange the terms. This equals to v over u. And this is actually streamline. How? So say here we are in a constant psi, so psi is constant here. So for this we know that, let's say we calculate a velocity vector here. So this is going to the velocity vector, say. So this is velocity vector. So this is, let's say, the v component, and this is going to be the u component of that. And then at the same time, you see here how much it is moving. We can, for this small element, we can say this is going to be dy and this is dx, right? So this is actually going to be the streamline, because for this psi equals constant, the dy over dx of that line, the psi, is going to be equal to v over y. So this actually means that we are moving over a streamline, on the streamline of the velocity. By a streamline, we mean if, for example, you have a particle and you let it go, this will form a streamline in the flow, right? And so we are actually now in a streamline of the flow. So psi constant is actually meaning a streamline. So these psi's, the constant psi's, actually represents the streamlines in our flow. Okay, so this is an interesting property of stream functions, and that's why we call them stream functions, because these functions actually represent the streamlines in the flow. Okay. So the second property of psi is that if you subtract two stream functions, two values of the stream function from each other, say psi2 minus psi1, this will show the volume flow rate between those two streamlines. Between those streamlines. How? Let's look at this property. Say here we have a streamline or psi, a constant psi2 here like this, an arbitrary one. And then here we have another one. So this is, let's say, the velocity is this way. And then we have another streamline like this. And this is psi1. Okay. So say I want to calculate how much volume flow rate is going between these two streamlines. So say then I'm going to start from point A in the flow, and then I want to see how much of the flow is crossing this AB line, which is between these two streamlines. Okay. So here, say for any arbitrary point here, we are going to have two velocity components, one u in the x direction, and then one v in the y direction, okay? So now I want to calculate how much of this flow is crossing this AB line, okay? So let's see, we have here, I'm going to plot this again. At that point, we have this u and v. And so this is like our streamline, the something between those here. I just zoom here, so I just zoom it here because I want to show other things. And then here we have dy. Say if we consider a small element here, and this is dx, okay? So now, how much of the flow is going through this dx and dy? Okay, so you see, we can decompose it into two parts. So for the element dy, right, which is going to be this element, so first of all, we want to calculate this mass flux that is going over this, right? N dot V, okay? And N is going to be always in the other direction, right? It's going to be in the outflow. So this is like N is going to be this direction, okay? Just so you know. So I wanna simplify this. So I just wanna look at each component separately. So for y, dy, the velocity component that is actually crossing this dy element is u, right? The u velocity is actually crossing this, because the v component is like this, so it's not actually crossing that that element, okay? And this is an outflow. Okay, so yeah, so I think I just the way we do it, we just say n is in this direction because we want to see how much is crossing that. So this is kind of outflow going out of this AB, okay? And then the other one is dx. So let me plot that. So this is the x component. And then for dx, the only velocity component that is actually crossing that is v, right? So this is the v velocity component. And this is going to be inflow, right? Because this is going out, u is going out here, as you see, and the v component is going into this say cross line or an arbitrary control volume that we have considered here. Okay, so one is outflow, which is going out of this, and one is actually inflow, which is going inside. And we wanna calculate how much of it is actually crossing here. So what is the volume flow rate which is going out of this AB line? Okay, so the volume flow rate, we can calculate it from line, we can integrate from line from point A to B of this n dot v ds over this streamline. So it's going to be first the rate of outflow, how much is going out. So it's going to be the integral from A to B of u times dy, right? This is how much is going out of this AB line. And then the inflow, we need to have a negative direction. We need to have a negative sign here because it's going inside this. So it's minus the integral from A to B of v dx. Okay, this is how you calculate the volume flow rate that is going out of this AB line. And what is this? Just look at it. We already had it. Minus v dx plus u dy. So let me rewrite it again. So this is the integral from A to B of minus v dx plus u dy. What is this? Here we have it. It's just d psi. So it's going to be the integral from A to B of d psi, which is going to be what? Which is going to be psi at B, which is psi 2, minus psi at, I can write it like this, psi at B and A, which is going to be psi 2 minus psi 1. Okay? So actually, this is what we meant and what we showed, that the difference between the streamlines is just a volume flow rate that is flowing across these two streamlines. So this is a very interesting property for stream functions. Okay. The next property that I want to show is lines with psi constant and phi constant. Now we also have phi constant are orthogonal. Orthogonal. They are perpendicular to each other. So let's show this. What is d phi? So d phi is from the velocity potential from last time. If you remember, we already had it, we defined it. It's going to be in a 2D flow. We can just, it's again function of space, so it's going to be partial phi over partial x dx plus partial phi over partial y dy, which is going to be, for the velocity potential, partial phi over partial x is u, so u dx, and partial phi over partial y is v, so it's v dy. And let's say for a constant one, so 0 is going to be 0. So phi is constant, this is going to be 0. Okay, so this means that for this function, for constant phi's dy over dx is minus u over v. And for a constant psi, this was v over u. So if you multiply this together, you're going to get minus 1. So this means that they are orthogonal to streamlines. And we talked about this, that they are orthogonal to the velocity vectors, which are kind of these streamlines. So let's have a quick example here, a short example for source flows. This is how it looks like. We already had it, I think. So let me show it here. So this was for a source flow, we had these velocity potentials, phi 1 and phi 2. Let me put it here again. Okay, so one is phi 1 and the other one is phi 2. Phi 1 and this is phi 2, and this is going to increase. And what are the streamlines here? The streamlines are going to be, or the size are going to be just these lines. These are just psi. This is psi 1 and this is psi 2. And these are all just different streamlines, which are just stream functions here. Okay, so this value is, if you want to calculate the streamline, the volume flow rate between these 2 points, you just need to subtract psi 1 and psi 2. Okay, this is how it actually looks like. These stream functions and stream and potential velocity potentials are orthogonal. It's very interesting and important point here. And the last property that I want to mention in this lecture about stream functions is that if the flow, in addition to incompressible and 2D, two-dimensional flow, is also irrotational. So we didn't have the irrotationality requirement for having a stream function, but just imagine if it is also irrotational, then this means that the curl of the velocity vector should be 0. So in 2D flows, this means that only component, which is going to be in the z direction, which is the k component of that. And I can find it. Where is this? Yeah, we can maybe look at it here, because it's only x and y. So this is going to be the only component here. So it's going to be partial v over partial x minus partial u or partial y. This is going to be the only component of that. So partial v over partial x minus partial u over partial y of k. This is the only component for that. So this has to be 0. So partial v over partial x minus partial u over partial y should be 0. And let's see what is that in terms of stream functions. Let me copy this here so we see based on that. So u is just partial psi over partial y, and the other one is, so I can write it as minus partial over partial y of partial psi over partial y, and the other one is v is minus partial psi over partial x, so we have partial over partial x of minus partial psi over partial x equals to 0, which means that partial square psi over partial x square plus partial square psi over partial y square equals to 0. And this means that this is actually the Laplacian. So grad square psi is going to be 0, or the Laplacian of stream function is going to be also 0, and this is going to be also linear. So this is also linear. So if the flow is also irrotational, then the stream functions are going to be linear, and we can find a linear relation for that. We can simply find an analytical solution for that. Okay. So in the next session, I'm going to use this property and then define both psi and phi for a particular type of flows, which are 2D irrotational incompressible flows. And then based on that, we can solve some analytical form of some canonical flows like potential vortex or other things in the flow. And this is a very useful technique to solve and find the analytical solutions of these flows and find these velocity potentials and streamlines in the flow. Thank you very much, everyone.